Section: Introduction. In this section, we will discuss the challenges faced by large language models, LLMs, in terms of memory bandwidth bottleneck during autoregressive decoding. The main issue lies in the time taken for memory read-write operations of model weights rather than actual computations. To tackle this problem, speculative decoding, SD, techniques have been developed to speed up autoregressive decoding by checking multiple tokens generated by a draft model simultaneously. The effectiveness of SD depends on two key factors: the difference between the draft model and the target LLM, and the inference speed of the draft model. Several studies have proposed self-drafting methods like LLMA and REST, which generate draft tokens without relying on external drafter models. However, these methods still face challenges. For example, while Medusa can generate multiple draft tokens efficiently, its token acceptance rate is not optimal. Focusing solely on token acceptance rate without considering the latency of generating draft tokens can lead to suboptimal acceleration. Lookahead, on the other hand, achieves a high token acceptance rate but lags behind Medusa in generating draft tokens efficiently. To address these challenges, we have developed Kangaroo, an autoregressive self-draft model that includes a lightweight adapter module on top of a fixed shallow subnetwork of the original large LLM. Kangaroo utilizes an early exiting mechanism to generate draft tokens more efficiently, avoiding unnecessary computational costs on complex tokens. Our experiments on SpecBench demonstrate that Kangaroo outperforms existing methods like Medusa 1 in terms of speedup and parameter efficiency. In summary, Kangaroo offers a cost-effective approach to training a lightweight small model for accelerating large LLMs. By sharing some cache and computation with the large LLM, Kangaroo only requires a small adapter network for deployment. Our paper is structured as follows. We review related works in Section 2, introduce Kangaroo in Section 3, present experimental analysis in Section 4, and conclude in Section 5. Section Summary. In this section, we introduce the concept of speculative decoding, SD, as a technique to accelerate autoregressive decoding in large language models, LLMs, by verifying multiple tokens in parallel. To address the challenges of SD, we propose Kangaroo, a self-speculative decoding framework that utilizes an early exit mechanism to efficiently generate draft tokens. Kangaroo outperforms existing methods like Medusa 1 on SpecBench, achieving up to 1.7 times speedup with significantly fewer additional parameters, making it a cost-effective solution for training lightweight small models. Section: Kangaroo. In this section, we will explore the detailed analysis of token acceptance rate, compression rate, and speedup ratio for various self-drafting algorithms. We will then introduce our framework, Kangaroo, which utilizes self-speculative decoding by sharing a fixed shallow subnetwork of the large LLM. To decrease the inference latency of the self-draft model, we will introduce an early exiting mechanism when generating draft tokens. We use different notations to represent token sequences and model the autoregressive process of a language model. The large target language model and the speculative small model are denoted as M(B) and M(S), respectively. Speculative decoding is commonly evaluated using wall-time speedup ratio and compression rate metrics. The compression rate is calculated based on the accepted tokens per forward pass of the large model. We propose a new metric called consistent token acceptance rate to better evaluate the acceptance levels of the drafting algorithm for tokens at different distances. Early exiting involves extracting hidden states from a fixed shallow subnetwork of the target LLM and learning a mapping to the final layer. We train an adapter network to connect the self-draft model and the target model. Dynamic drafting steps with early exiting aim to adjust the drafting step during the drafting phase to avoid local optima and save latency. We conduct experiments on vicuña models and compare different self-drafting speculative decoding approaches using compression rate and wall-time speedup ratio metrics on NVIDIA V100 GPUs. Section Summary. In this section, we analyze token acceptance rate, compression rate, and speedup ratio of self-drafting algorithms before introducing our framework, Kangaroo, which utilizes self-speculative decoding with a fixed shallow subnetwork of a large LLM. To enhance the inference latency of the self-draft model, we introduce an early exiting mechanism during token generation. Kangaroo also incorporates a lightweight adapter network to connect the self-draft model with the target model, improving efficiency and reducing training costs. Section: The depth of shallow subnetwork. In this section, we analyze the depth of the shallow subnetwork in our self-draft model, M(S). The performance of our model relies heavily on how deep the shared shallow subnetwork is. We need to find a balance because choosing deeper early exiting layers, like half layers of M(B), can cause long inference times. Therefore, the early exit layer L helps us balance between accepting tokens quickly and drafting efficiently. For example, in Vicuña 7b, we set L equals 2, and in Vicuña 13b, we set L equals 3. Moving on to the adapter module architecture, in a transformer block, the FFN component makes up 67% of all parameters. By removing the FFN component and sharing the LM head of the target LLM, we see a significant improvement, as shown in the table. Next, we compare dynamic exiting with fixed-step drafting to see which is more effective. We plot this comparison for different values of eta in the figure. The fixed-step strategy, eta equals O, gives us the highest compression rate, but it may not be the fastest in terms of end-to-end wall time speedup. Interestingly, the optimal threshold eta remains consistent across various maximum steps. For Kangaroo, we set gamma equals 6 and eta equals 0.6.